this video, we are going to explain about the project title, A Multi-Stage Machine Learning and Fuzzy Approach to Cyber Hate Detection. Introduction. The emergence of social media platforms facilitated global connectivity, enabling people worldwide to communicate effortlessly. However, the borderless nature of these platforms also brought forth a significant downside, the growth of cyber hate. Geographic barriers dissolved, leading to a surge in hate speech, discriminatory content, and abuse behavior. This widespread issue posed a challenge as traditional methods of managing hate speech, like manual flagging, were unable to cope with the sheer volume and global reach of online hate. Manual flagging systems relied on human moderators to identify and flag inappropriate content, but they struggled to handle the vast amount of data generated on social media platforms. These methods were slow, limited in scale, and often unable to detect subtle or evolving forms of hate speech. Thus, the inadequacy of these traditional approaches necessitated the exploration of automated detection methods. To address these challenges, the project proposed an optimized machine learning based approach. It leveraged sophisticated techniques such as multinomial naive Bayes and logistic regression, which are commonly used classifiers in text analysis. Additionally, it integrated genetic algorithms and particle swarm optimization, which are bio-inspired optimization techniques. This amalgamation aimed to enhance the accuracy and efficiency of identifying and categorizing instances of online hate speech. A key emphasis of the project was on refining the machine learning model. By reducing redundant features and irrelevant data points, the framework aimed to improve the model's accuracy and interpretability. This process of feature selection and optimization was crucial for creating a more effective and efficient cyber hate detection system. Fuzzy logic systems were integrated into the framework to address the inherent ambiguity and nonce present in online content. They allowed for the handling of non-sentiments by capturing the fuzziness in positive and negative scores. This incorporation aimed to achieve a more refined understanding of the subtleties in language, enabling a more accurate identification and interpretation of hate speech. Objective. The primary aim of the project is to create an advanced framework using machine learning techniques, particularly optimized for detecting instances of cyber hate within online messages. It incorporates fuzzy logic techniques to enhance the precision of identifying hate speech, considering the nuance of language and sentiment. The project plans to employ various machine learning classifiers, notably multinomial naive Bayes and logistic regression, recognized for their efficiency in text classification tasks. Alongside these classifiers, the project integrates bio-inspired optimization techniques like genetic algorithms and particle swarm optimization. These techniques aim to refine the classification process, improving both accuracy and interpretability of the model's outcomes. Another key aspect of the framework involves streamlining the classification process by minimizing redundant and less impactful features. This process of feature reduction significantly enhances the efficiency of the model as it focuses on the most relevant data points for effective cyber hate identification. Fuzzy logic-based systems are integrated into the framework to account for the ambiguity and subjectivity inherent in human interpretation of online messages. These systems capture the fuzziness or uncertainty in positive and negative sentiment scores, aiming to present a more realistic representation of how people perceive and interpret online content, especially regarding hate speech. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules of flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages required for data analysis, natural language processing, machine learning, and visualization. Commonly used packages include pandas, NumPy, Matplotlib or Seaborn for visualization, sklearn for machine learning. Exploring the dataset, cyberbullying data. This phase involves gaining familiarity with the dataset related to cyberbullying. It includes tasks such as loading the dataset, checking its structure, number of rows, columns, understanding the features or columns present, checking for missing values or inconsistencies, and getting insights into the nature of the data specifically related to cyberbullying. Visualization. This module involves using graphical representations like plots, charts, or graphs to visualize patterns, distributions, correlations, or trends within the cyberbullying dataset. Visualization aids in understanding the data's characteristics, identifying potential relationship between variables, and gaining insights that might be hidden in the raw dataset. Data pre-processing. Removing the URL and other characters. This step involves pre-processing the text data by removing URLs or special characters that might not contribute to identifying cyberbullying content. Remove punctuations. It entails eliminating punctuation marks from the text data which are not significant for the analysis of the message content. Remove stop words. Stop words are commonly used words like and, the, etc., which may not add substantial value to the analysis. Removing them helps in focusing on the more meaningful words. Normalization. Normalizing the data involves converting text to a uniform format, like converting uppercase letters to lowercase, ensuring consistency in the representation of words. Tokenize the words and lematize words BOW, bag of words. Tokenization is the process of splitting text into smaller units, typically word or phrases, tokens. Lemmatization involves reducing words to their base or root form. In bag of words BOW, tokens are used to create a representation of text for machine learning models. Vectorize the text. Vectorization is the process of converting text data into numerical vectors that machine learning models can process. These techniques like TF-IDF, term frequency inverse document frequency, or count vectorizer are often used to transform text data into numerical representations. Feature extraction. This step involves extracting meaningful features from the pre-processed text data that can be used to train machine learning models. These features include word frequencies, TF-IDF scores, or other statistical representations derived from the text. Feature selection. Feature selection involves identifying and selecting the most relevant features that contribute significantly to the predictive power of the model. It eliminates less informative or redundant features, thereby improving model efficiency and reducing overfitting. Splitting the data to train and test. The dataset is divided into two subsets, a training set used to train the machine learning model and a separate test set used to evaluate its performance. This ensures that the model's accuracy is assessed on data it hasn't seen before, validating its generalizability. Building the model. This step involves constructing the machine learning model using the pre-processed feature engineered data. Commonly used models for text classification include Naive-Bayes, logistic regression, etc. Training the model. The model is trained using the training data to learn patterns and relationships between features and labels, cyberbullying or non-cyberbullying content. Flask framework with SQLite for sign-up and sign-in. Flask is a web application framework used for developing web applications. SQLite is a lightweight database often used with Flask. This module focuses on creating a user authentication system where users can sign up and sign in to the platform. User gives input. When a user inputs text for analysis, the text undergoes pre-processing steps similar to those applied during the model training phase, removing URLs, punctuation, stop words, normalization. The pre-processed text is then fed into the trained model for prediction, determining whether the input contains cyberbullying content or not. Trained model is used for prediction. LDA, latent Pentagonal allocation is a popular technique used for topic modeling. It helps in identifying relevant topics within text data. This module focuses on extracting underlying topics from the dataset, potentially revealing themes of relevant subjects in the text. Final outcome is displayed through front end. The results of predictions generated by the model along with the insights from the LDA model are displayed to the user via user-friendly front-end interface. This interface provides an intuitive presentation of the analysis outcomes to the end users. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is Naive Bayes. Naive Bayes is a probabilistic classifier that assumes feature independence. It calculates the probability of a text belonging to a specific class such as hate speech based on the presence of certain features, example words, phrases. In this project, Naive Bayes is used to analyze text features and predict whether they indicate the presence of hate speech. Logistic regression. Logistic regression is a linear model used for binary classification. It predicts the probability of a text belonging to a particular class by fitting the data to a logistic curve. In this project, logistic regression is applied to classify text as hate speech or non-hate speech based on the relationships between text features and class labels. Naive Bayes fuzzy genetic algorithm and Naive Bayes fuzzy PSO, particle swarm optimization. These methods extend the Naive Bayes classifier by incorporating fuzzy logic along with genetic algorithm GA and particle swarm optimization PSO. Fuzzy logic allows for handling uncertainties, while GA, genetic algorithm, and PSO, particle swarm optimization, optimize the classifier's parameters or perform feature selection, aiming to improve its precision in identifying cyberhate instances. LR fuzzy GA and LR fuzzy PSO. Similar to the NB extension, these methods combine LR with fuzzy logic GA, genetic algorithm, and PSO, particle swarm optimization, to enhance its performance in detecting cyberhate by optimizing parameters or selecting relevant features using fuzzy logic. Voting classifier. This ensemble technique combines predictions from different Bayes models such as AdaBoost AB and Random Forest RF. AdaBoost focuses on boosting weak classifiers, while Random Forest builds multiple decision trees. The voting classifier aggregates these predictions to make a final decision about whether a text contains cyberhate, leveraging the strengths of each Bayes model. Stacking classifier. Stacking involves using predictions from multiple models, that is NB, Naive Bayes, logistic regression, AdaBoost, Random Forest, has features for training a meta-learner. This meta-learner then produces the final prediction. In this project, the stacking classifier utilizes predictions from various models to make a more informed decision about the presence of cyberhate in a text. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graph. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the F1 comparison graph. On the x-axis we have the F1 score, and on the y-axis we have the algorithm name. F1 score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is the model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here, I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and then paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and then hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first, so click on sign up button. So here we need to enter all these details to register, but I have already registered, so click on sign in. So here we need to enter the username and the password which we have registered, and then click on login. So here we have logged in successfully. So here we need to enter the message, and after entering the message, we will predict whether that message is cyber hate or not. So here I have entered this message. Now click on predict. So here we can see we got the results for the comment. Label, the text type is cyber hate content. The topic for the paragraph is most dependent upon these words. Now let us enter some more messages and check whether the text type is cyber hate content or not. So here I am entering some more messages now. So here I have entered one more message. Now click on predict. So here this is the message which we have entered, and the label is the text type is cyber hate content. The topic for the paragraph is most dependent upon these words. Now let us enter some more messages. So I'm entering one more message. So here I have entered one more message. Now click on predict button. So here we can see this is the message which we have entered, and the label for the message is the text type is not cyber hate content. The topic for the paragraph is most dependent upon these words. So in this way, just by entering the message, we can predict whether the text type is cyber hate content or not. Now click on sign out button. For the project is, this signifies the project's approach to employing a multi-layer system utilizing machine learning concepts along with fuzzy logic for cyber hate detection. It aims to create a comprehensive system that accounts for the complexity and ambiguity often found in online content. This highlights the utilization of different classification algorithms like multinomial Naive Bayes and logistic regression, known for text classification tasks. Additionally, genetic algorithms and particle swarm optimization were applied to optimize the parameters or structures of these classifiers, aiming to improve their effectiveness in identifying cyber hate content. Fuzzy logic systems were integrated into the framework to account for the subtleties and nonce in online content. By capturing nonce positive and negative scores, these systems aim to emulate human interpretation, as human perception of sentiment often involves ambiguity and context. The utilization of bio-inspired optimization techniques like genetic algorithms and particle swarm optimization aim to enhance the performance of the classifiers. These techniques optimize the classifier's parameters or structures, thereby improving their accuracy in detecting cyber hate content and making their outcomes more interpretable. A focus on feature reduction aims to streamline the classification process by eliminating irrelevant or redundant features. This effort significantly improved the efficiency of the classification models, making them more effective in identifying cyber hate content.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.